Good morning and welcome to our second lesson. And this one is the easiest chapter in all of AP Chem. It's called Mass Spectra. So take a look at this. If you look at the periodic table, you will see that the mass number is never a whole number, which is weird because by definition, the mass number is the number of protons and neutrons in the nucleus. So if I take a look at my chlorine here, that means that I got 0.545% of proton or neutron in there. You cannot cut protons and neutrons like this in almost half. Not at least not in this regard. So in this context. So what does that mean? Actually, if you look at the mass spectrum here, this is a mass spectrum of chlorine. You see two peaks and two CLs, and this one says 35 CO plus. This one says 37 CO plus. Don't worry about the plus. A plus is there just because mass spectroscopy as a method has to include ions, positive ions. But we don't care about that because if you remove an electron to get a positive ion, you didn't do anything to the mass because the electron's mass is negligent compared to the mass of nucleus. So, but what you need to pay attention is they're both chlorine because they both have 17 protons. Because an element is defined by a number of protons, but not neutrons. So this one here basically has two more neutrons compared to this. When this happens, we call them isotopes. So it has the same number of protons, different number of neutrons. And this mass number in the periodic table is calculated by averaging these two out, but taking into account their abundance in nature. So this means that 75% of all chlorine in nature is chlorine 35, and 25% is this. And how do you get to this number is, first of all, you want to turn percentages into fractions. In 99% of the formulas in chemistry and physics as well, you don't want to use percentages because you have to divide by 100 at the end. So use fractions. How do you make a fraction? It's 75 divided by 100. So this is 0.75 and 0.25. And then you can simply calculate the mass number by multiplying 0.75 times 35, 0.25 times 37, and you get the average of 35.5. You could use percentages. You could write 75 here and 25 here, but then you have to divide everything by 100. And again, in every formula, that's going to be a problem. So just use fractions. Also, don't worry that this number is different than this number. It might be a rounding. It might be that they rounded differently. They measured with more precision. In some periodic tables, they will use isotopes that are not in the book because the book is not, from 5 years ago and new isotope was discovered. So this small difference is not of consequence. You shouldn't pay attention to that. What I do want you to pay attention to is this, and it's a very annoying thing. See, you get all of these types of representing the mass spectrum in the AP curriculum. And you shouldn't pay much attention to this. Take a look at this. On the x axis here, it says mass per charge. This is also mass per charge. This is just M through Z, which is also mass per charge. And here is AMU. We talked about AMU in the last video. So you don't need to worry about this because all of this is just for our intents and purposes, just the mass number. So you can see this is a mass number. This is also a mass number. It is. Atomic mass is a mass number. And mass per charge in charges plus one is just a mass number, but in grams. However, units here don't matter. You won't even see units anywhere in here. So they don't matter. Also, on the y-axis, don't get confused by this. This is relative abundance in percent, which means that if you add all these peaks, they will add to 100. But this is relative abundance without percentages, which means that if this one is double, this peak is double sized to this one, then the abundance of this 29 is double abundance in 30. But you don't really need that. You will see. So these questions about mass spectra are best done by estimating. You don't want to calculate because, again, this is in multiple choice questions and you won't have much time. So let's try a couple and see. Take a look at this. This is a very easy one. So you can see that the mass number is here is something close to 11, but a little bit less because there are two isotopes and this one is at 10 but much less abundant. So this is 10.8 or 9. And if you check at the periodic table, you'll notice another thing. The mass numbers are pretty different. So this one is 1, and then if you go from left to right, this is 4, 7, 9, 11, 12, 14, 16, 19. So there is a big difference between them. So what I'm looking for now is something close to 11, but a bit less. It can't be this. This is 9. There's nothing at 9. 10.8, probably, but let's see the other option. 12, no. So this is obviously boron. You don't want to calculate. You could technically use a ruler or try to read this here and actually calculate a pretty precise mass, but I mean, you don't want to do that. You want to do it quickly. So yeah, this is just boron. Let's take a look at this. This is a bit more complicated, but still, again, 3 points. 24, 25, and 26, 3 isotopes, but the one at 24 is way more abundant. So this is something just about 24. Let's see what we've got. You got this one, 24.3, possible, just about 24. This is 23, right? There's nothing there. And this 27, there's definitely nothing at 27. So this can only be Mg, yes. This one I wanted to show you right away. It's pretty complicated, but it's easily doable still. So you've got 7 isotopes. You can see this is exactly in the middle, 96, right? And then if you go left one step, it's going to lean towards 95. Why? Because this is bigger than this. But if you go the second step, this is way bigger. So now we got something above 96, right? But then if you compare these two, it's pushing backwards again. So I will say this is for sure something between 95 and 97, right? So let's see what options we've got. 91, 92, wait, 93, not possible, right? There's nothing in 93. 96, possible, almost exactly in the middle. This is 98, not possible, right? So this is for sure correct. Molybdenum. I can't possibly spell that. Let's take a look at this. This one is pretty cheeky. It's the most difficult we can get from here. It's kind of misleading. So this is the highest abundance, right? However, all of these are pretty far away to the right, especially this is going to pull it to the right. And if you add these together, they're going to add up to almost this much, right? So this is not 90. Could be something from 91 to, I don't know, 92. Can't be anything in 93, right? Because if it's in 93, you can see that, I mean, there's way much stuff on this side still. So 91, 92. Let's see what we've got. Wait, this is 89. Not possible. 91.2. Pretty okay. 92.9. I don't like that because that will have to be here. And if you put it here, you can see already that there's way much stuff on this side. So this will have to be zirconium. That one I can spell. Only in Europe it's spelled zirconia, as far as I remember. Ooh, we're correct. I think there's another one. Yeah. This one is a bit different. This is part of a free response type question. So basically, they gave you these 3, and they told you that you need to find which one of them is iodine. Which one of them is iodine? So now you can just look at the periodic table again. Iodine is 126.9. Let's say in 127. So can't be this one because this is going to be 126 point something. Can't be this one because this is exactly 126.5, right? The average. Can't be this. This is almost 197, 127, sorry, but not quite. Yeah. So easy peasy, and I mean, I already gave you the answer. Okay, try to do these and let me know if you need any help. See you soon. Bye bye.